RISE event, so Retrofit Information Support and Expertise, and it's fully funded by the Department of Energy Security and Net Zero, and it's delivered by Turner and Townsend, today specifically Julian, but thank you.
Okay, thanks, Sophia. Yeah, hi everyone, let's kick off. So a quick short agenda for today's session. Just looking at the context for EPC, a quick example, sort of measures that you might be looking at installing on your property portfolios or target dwellings to get you to the EPC C target, which is what the government-funded warm home schemes are aiming at, and then further considerations. So about EPCs, so really what they're about, they are showing the energy performance of a home on a relative scale. They look at the building fabric. So an EPC assessment basically will look at the building fabric, walls, windows, roof, doors, etc., looking at the kind of, if you've got double glazing, if you've got insulation in place, etc., etc. And then it will also look at the heating systems, any renewables, the type of lighting you've got, etc., etc. And it comes up with a score for that on a scale from 1 to 100. And you can see from that banding on the right there what an EPC C is. So it's covering scores from 69 to 80 inclusive. And basically, so that's this kind of sweet spot, as they would say, for improvements of properties up to that point at which you would, in an ideal world, then be looking at low carbon heating systems to decarbonize properties completely. But basically that is the target for an EPC C. As I say, the EPC doesn't cover just fabric measures at all. It covers your heating system and what kind of lighting, LED, CFLs or incandescents or whatever you might have in there, and any renewable systems. You might have solar thermal heating system, for instance, or an air source heat pump there already. EPCs are valid for 10 years, and they do make recommendations for improvements. So this is the surveyed measure, giving whatever this property is a score of 39 and a category E, and they're saying that potentially with certain improvements to various elements, you could put that up to a 72 score for a C. That's just in this example. So the EPC shows a few things, not everything, and the idea of it is it's really meant to be showing you a kind of cost for running the house. Now, that's a relative term, as we know, certainly within recent years, costs of energy have fluctuated quite wildly. So really, I suppose an energy demand would be a kind of more accurate kind of prediction. It doesn't take into account the occupancy, so if you have say a young couple who are living in a property who are out all day at work and only come into for the evening and maybe at home at the weekends, that's one level of energy use. If you had a young family, possibly with someone from an older generation, grandparent living with a family, then you would have a completely different type of energy profile for that property, for the same property. So EPCs don't give you a measure of energy use. They give you a sort of modeled measure of the kind of efficiency of that property, given the systems and given the fabric that property consists of. So yeah, in this property, we've got estimated energy needed in the property is the 1920 kilowatt hours per year for heating, and then the 1437 kilowatt hours per year for hot water. So basically, these are the kind of things that you really need to know when you're trying to understand how to, I suppose, model improvements across a portfolio and the kind of carbon savings you can expect from the introduction of various measures. So it's really in simple terms, we've got model energy use and costs, estimated future costs, but that's obviously based on a kind of given price for a kilowatt hour of energy, suggested improvements, and then the estimated current from future carbon emissions, which is also fluctuating because of the carbon intensity of the grid. Now that is all about how much we have in terms of renewable power on the grid at any one time. So certain days of the year can be much less carbon intensive than others. In the winter, we might have more wind power on the grid, obviously much less solar. But yeah, the carbon intensity of the grid is coming down as more and more renewables are built and introduced to the grid. So when might you need an EPC? So compliance. So this is a legal requirement whenever you're selling or renting a home. And we have the minimum energy efficiency standard for landlords, which also requires a valid EPC. Grant finance, so typically Warm Homes grants for Social Housing Fund or local grant, SHDF before it. So the grant funding, government grant funding, will require properties that are being improved to have a current EPC, and therefore you're basically targeting properties which are below an EPC C in order to improve them up to that level. Environmental considerations, so having an EPC for all your properties can certainly help with decarbonisation plans. It's a little bit like having good data on your estate. Basically gives you an idea of what the kind of energy demand of these properties is and the carbon usage associated with that. Asset management, obviously, if you've got properties that include maybe a condition survey, maybe information about boiler changes, window upgrades, anything like that, but also EPCs. It just adds to the quality and depth of information you have about properties on your portfolio. And for customers, obviously it does provide a degree of transparency. If you have tenants in place and they're in fuel poverty, and they are in maybe an old solid wall property with a very low EPC rating, they can see that property, is going to cost them an awful lot in terms to maintain any kind of comfort internally, and that obviously will be something that can be a good use of targeting for improvements. So just thinking about the EPC C target, it might be that with the Warm Homes grant, obviously, that you may be utilising to improve that money, to use that money to improve it to a C, but maybe you as a landlord, as a property owner and manager would want to go beyond that. It depends on the kind of policy you might have as a social landlord, as someone who's managing a portfolio of social housing. So you might within your own kind of organizational policy have other targets that you want to address. Maybe you have heat demand targets, so particular heat demand of a dwelling, say 50 kilowatt hours per square meter per year. Or you might have particular standards like Enefit, which is a passive house retrofit standard. These are some of the different categories of targets that you might have on the right there. So just when we are thinking about properties which have a low EPC rating, what does that imply? Well, expensive heating, not expensive heating systems, it's expensive heating costs, really. We know that a low EPC will be indicative of, could be a poor heating system, an old one that's inefficient and relatively costly, and it can also indicate that you've got poor performing windows, doors, little insulation in place. So basically, you've got a property which leaks heat. You're kind of heating the outside as much as you're heating the inside, and the heat will leave the building very quickly through the walls, through air gaps, etc., etc. So in essence, it's a much more costly property to maintain any level of comfort inside. That point at the bottom there, it's a much higher risk of maintaining a situation of fuel poverty for the residents in these properties. Hard to treat archetypes, they're solid wall and certain system build properties, classified as hard to treat in the sense that they are treating solid wall properties is much more expensive than filling cavity walls with insulation in simple terms. So they're categorized as hard to treat. A lot of the older properties as well still have original single glazed windows, which are also obviously very thermally inefficient. And a lot of the systems, it might be indicating that your systems are out of date in the property. So old boilers, old lighting, you might still have quite a bit of, incandescent lighting. It's still available. And maybe old water tanks that aren't insulated, that kind of thing. So it's basically indicating properties which are expensive to heat and light, and so very costly to those residents. So how do we get to EPC C? You really need to start off with good data for your property in terms of as a baseline. So stock condition survey, potentially maintenance, asset management schedules and programs, anything to do with when improvements might have been made in terms of window programs, boiler programs, that kind of stuff. And having an EPC valid for the property so you know where you are starting from. Technical support to be able to do cost analysis. So you might need some sort of modeling available to you to be able to take this data and look at how you can get to as many of your properties to EPC C as possible for least cost. And then also the third element you will be needing to think about is in terms of applying for grants, is having the resource to do that. So bring all this data together, model what it is you're going to do with your properties to get to EPC C, and applying for the money and going through the whole process of gathering all this. It does take quite a lot of effort. So you would have heard the term probably fabric first. There are a few other terms going around as well, like fabric fifth. But fabric first is basically the kind of approach that PAS 2035, which is the quality standard for retrofit, takes. And the idea is that you reduce the thermal losses from a building as much as is reasonable before you then put in a low carbon heating system, which is then sized to that demand, the lower demand. If you look at the pie chart on the left, it looks at kind of the heat demand for a typical property. So you've got 70% for space heating and just over 12% for water heating. So if you think about it, that is all coming from your boiler. So the efficiency of your boiler and the condition of it really has a big impact on the energy use of that building. You've got other appliances at just under 10, cold, so fridge, freezer, about 2.5%, lighting and cooking as well. But they're all relatively small amounts compared to the water and space heating demand. On the right there, you're really looking at the kind of the generic the sort of idea of the kind of heat losses from different elements of a building that you would typically expect. So basically, when you reduce this through fabric improvements, so insulation to the loft, to the walls, floors, maybe improvements to windows and doors in terms of drafts, but also in terms of the actual performance of the windows and doors. Once you've reduced that heat loss, then you would think about replacing certainly the boiler, but possibly boiler with a smaller, more efficient boiler, but also potentially with a heat pump of some kind or some other, maybe connecting to a low carbon heat network or other options. So just thinking about looking at sort of example of an EPC that's been rated as C and the kind of information that you would get on this EPC. So as you can see on the right here, well, on the left, we've got an E rating of 49 with a potential of C 76. And then over on the right here, we're looking at the kind of performance of different elements within the house that are existing. So the walls here, a cavity wall has built partial insulation assumed. So someone hasn't actually drilled a hole in the wall and put a borescope in there and looked to see. They might see that there are drill holes in the wall. So it's a kind of telltale sign of some kind of cavity wall insulation has been installed. And there's an efficiency rating there, which is just a visual kind of sign to say that it is assumed that this has a certain level of useful energy efficiency. The roof here is pitched. Someone has looked and seen that 75 milliloft insulation in there, which again is certainly better than nothing, but the standard at the moment is 270 millimeters is the optimum level. Floor solid, no insulation assumed. Again, the assessor hasn't drilled through the floor to see if there's any insulation underneath. They would assume maybe from the age of the building and other visual signs that they might be looking for that this floor is not insulated. Windows, so partial double glazing. Again, it would be good to know that the windows are double glazed throughout, and maybe there's a certain reference number on those windows to give you the energy performance of them. But these are assumed to be obviously only partial double glazed. And so you can go through the other kind of elements and what their relative performance is. So these are the recommendations that this EPC would be looking at. So as I mentioned, you can top up that 75 mil to 270 mil indicative costs, savings per year, and the rating improvement. So it would be bumping that up in its first stage. So these are the kind of, I suppose, the low-hanging fruit in a way, the easy ones you would start with at the top and then working your way down. So the savings per year indicated here, and the cost of the actual installation indicated here, and this is how you would progress to that target of 76 and a C. You could obviously stop at 74 and C, in that sense of it being, it's got to the target, you might say, and that would be perfectly valid under one of the government schemes. So just thinking about the kind of common improvement retrofit measures, improving the energy performance of a building that you might typically be recommended through an EPC. Switching all lighting to light emitting diode is obviously the first one. It's easy to do, and LEDs use about 1/10 roughly of the equivalent of an incandescent bulb. And yeah, pay for themselves relatively quickly as well. Insulating a hot water cylinder, again, a jacket that goes around a copper hot water cylinder makes a big difference in terms of heat loss, and therefore the energy you're using to keep your hot water hot. Installed heating controls. So again, managing when the boiler is actually operating to heat your internal space, and having good heating controls that aren't just on off at certain times, but can be controlled for different temperatures in different rooms, do make a difference. It's it's surprising how many people almost use their thermostat as an on-off switch, and obviously it's not the way they're designed to be used, and certainly won't give you the maximum efficiency of your heating system if that's what you're doing. So installing a good quality heating control, and obviously something which is relatively easy to understand how to use it. Replacing the boiler with a new condensing boiler, that would be, I mean, obviously we have the gas boiler replacement deadline, and really through government schemes there would be an encouragement for boilers to be replaced with heat pumps or other low carbon heating systems. But within the EPC, the replacement would probably be a recommendation for a new condensing boiler. Again, replacing single glaze windows with double glazing, very common sort of install. Upgrading loft insulation, replacing inefficient electric heating. There are some very much more better performing storage heating systems than some of the traditional ones that you will find in properties. So installing wall insulation to solid walls or cavity walls, and solar panels, again, you know, they were a lot of solar panels were installed with grants and when FITs were available as well. And that note at the bottom, fabric still remains a priority. Just a quick recap about wall types. So when you see this kind of brick pattern on a wall, where you can see the header ends and the stretcher lengths mixed along a wall, then that shows you it's likely to be a solid wall, or it's indicative of solid walls, because the header of the brick is basically showing that a brick has been laid lengthways through the wall. So that's a solid wall configuration, and there are a few variations on these in terms of, you know, whether the headers are every row of bricks, every course of bricks, or maybe every third course of bricks or whatever, but that kind of pattern indicates a solid wall. Cavity walls, you tend to see just the stretchers in this kind of traditional brickwork pattern, because they've got this cavity between the outer and maybe the inner skin of bricks. So just a quick overview of types of wall insulation. So in terms of, we've got external wall insulation, EWI, internal wall insulation, IWI. So external obviously goes on the outside of the solid wall. Internal, inside, just on the external wall, and cavity wall insulation, which you inject from the outside into all the accessible cavities. So suitability, solid wall or narrow cavities, so that's less than 75mm cavities are called narrow cavities. And with cavity wall insulation alone, won't really give you enough performance from the wall, so you would probably use some cavity wall insulation and a thin layer of external or internal solid wall insulation as well. In terms of the disruption, external wall insulation is not that disruptive in terms of life going on inside for your residents, because the wall, most of the work is happening on the outside, might be scaffolding, etc. Internal wall insulation is very disruptive. It's basically going, whichever room you're doing, you're having to remove, in terms of the outside wall, you would need to be removing skirting boards, any radiators, any electric sockets, move the carpet a little bit as well to allow for 75mm of insulation, the stud wall in effect being built on the inside of your solid wall, and bats of insulation being inserted in between the studs, and then having some plasterboard and plaster finish put on top of that, and then refitting skirting boards, refitting carpets or any other floor covering, and reinstalling tails and a radiator and any other sockets that were on that wall. So it's not something you can do with someone actually carrying on using that room. So yeah, internal wall insulation is pretty disruptive. Cavity wall insulation, like I say, it's minimal disruption to occupants. So in terms of external wall insulation, the types are usually systems that different manufacturers will will produce, and they tend to train installers in how to use that system. Internal wall insulation is normally a sort of custom-made system where, as I say, it might be some kind of timber frame that is used to support insulation, roll type insulation in between the timber studs, and then a kind of a layer of plasterboard and a skim on top of that. Cavity wall insulation can be different types of material that are blown into the cavity via a sort of pipe and tube network into a nozzle through holes in the wall. So we've got polystyrene beads, it could be mineral fibers, it could be foams, it could be, different types of material that can be blown into that cavity. Other considerations: external wall insulation may well require some kind of planning consent. Certainly will do if it's in a conservation area. It requires good weather for the installation. Obviously, if you're putting wet render onto the outside of the wall, once you've got the insulation, you then normally have some kind of netting, and then a render system is troweled onto the outside, which does require good weather to cure. You also require good wall access. So that might be scaffolding, and if there's any kind of access down the side of a building where the walls are being insulated, that can cause problems of restricting the access. So that is another consideration. Internal wall insulation, obviously potential, well, there's lots of internal wall floor area, which depending on size of rooms might be quite an impact. Removal and reattachment of skirting boards, and I think you really should be considering things like sockets and radiators as well in here. There are other considerations around windows, whereby if you have a window with a recess, then you might well need to insulate that recess as well, and that can potentially impinge on the size of window, etc., etc. So there are all sorts of interesting details that need consideration when thinking about these solid wall systems or solid wall solutions. Cavity wall insulation, obviously you have to understand that you've got suitable cavity. It must have a damp-proof course, not have rubble in the cavity, and it needs to be damp-free. There's quite a lot going on at the moment to remove old cavity wall insulation, which has become damp. And once it's damp, it's worse than having no insulation in there, because it just allows moisture to track across the cavity and to the inner leaf of the cavity wall, and from there the moisture comes into the house. So you can, once this moisture has got trapped into a cavity where there is existing insulation, then there can be problems, and you might have to certainly proceed firstly with removing failed cavity wall insulation. This is just showing you what the internal wall insulation solution typically looks like. As I mentioned, you've got a sort of stud framework built up on the outside wall there. These kind of vats of insulation material, maybe a kind of mineral wool, and then you would cover that with plasterboard and skim it with plaster. The other approach is a rigid board. This is a Kingspan with a foil backing. So this is a phenolic foam board. And again, you would need to cover this with something like a plasterboard and then skim that plasterboard to give you a proper finish. Examples of external wall insulation, well, not examples, just an illustration. So on this house here, we can see that these polystyrene boards, EPS boards, have been mechanically fixed. These little white dots are the heads of mushroom-headed screws, long fixings that go through the plasterboard and into the wall, and they're normally installed with a knock of a hammer. They're like a long plastic fitting which goes into a hole in the wall, and then when you whack a pin with a hammer, it splays the internal fixing and anchors it into the wall with a mechanical kind of attachment. If there are gaps between the boards, they're often filled with expanding foam. You can see along these seams. Also, when it comes to other kind of fixings like external taps, gas meters, other kind of access points on the outside wall, you have to think carefully about how that detailing is done with external wall insulation. So it looks like there's some kind of pipe work, or maybe access to a guttering or a ground, trap of some kind down at the floor level. Up at the top, the eaves of this roof look long enough as well to cover the top of the insulation, so that's good. And it looks like there's a new soffit being fitted as part of this. On top of this, you would normally get some kind of mesh installed and then a render to match probably the properties either side of it. Window ledges, if you imagine the window, I mean, what would be good practice is to actually move this window out into the external insulation, into the insulation layer. It happens sometimes, more often than not, it doesn't. So in effect, you're putting another 100 millimeters out from the window. So you would need to have some kind of finish, on that kind of return to the window, and an extra window ledge, some kind of piece of material to act as an extended window ledge out beyond the new insulation layer. Just thinking about cavity wall insulation, this is a cross section of a typical cavity wall where you might have a block work inner skin and a brickwork outer skin, and then a kind of, as I said, sort of nozzle would basically, through a system of holes in the outer wall, would be used to inject, in this case, something called thermobead into the wall, which is like a polystyrene bead in a resin. The other ways, this is actually more of an illustration for new builds, but if you were blowing, say, mineral wool into the wall, this is the kind of, it wouldn't go in as blocks like this, but you would basically be blowing mineral wool into the gap. Again, I'm not sure you would necessarily want to do this with natural fibers such as a wool, because if you had any moisture going through there, the wool fibers tend to act as a bit of a sponge. And unless they're being treated with the right kind of water repellents, then you wouldn't want to be putting those in here. The polystyrene bead in resin can act as a barrier in here. So if you're getting rainwater penetration through, it meets the resin bead and just drains down the inner skin, and hopefully out of weep holes at the bottom of the wall. Just thinking about another measure, loft insulation. Again, a relatively sort of low-hanging fruit type of solution, relatively low cost, quite a good impact if you've got 75 mil or less of loft insulation in place. So you basically be topping up at the ceiling level here if you've got a cold roof. If you've got a warm roof, so that loft space might have some kind of usable space in it, then the insulation would go between the rafters of the roof on the roof level, as opposed to the ceiling level. And these are rough costs. Again, I'm not sure about the accuracy of those costs today, but it's a relatively low cost solution still. The important thing to think about in terms of cold roofs is maintaining a cross flow of, so where the insulation meets the actual roof layer, what you can fit here is there's some fittings which allow fresh air to pass under the roof line and across, and they're like a sort of extruded plastic panel with holes through it, and you can fit it on the inside of the roof and take your insulation right up to it. And actually within the plastic fitting there are air gaps to allow air to pass behind. Again, just a couple of illustrations there of the different types. So warm roof, you're putting your insulation between the rafters inside the roof, and on the cold roof, you're doing it at the ceiling level between the ceiling joists. When we're talking about flat roofs can be a little bit problematic, mainly in terms of making sure that they have a good water seal after the works are done. But again, you've got two different types here illustrated here. There's a warm roof where you're putting the insulation on top of the roof. So basically you have the timber joists, you have a plywood layer. The old roof would have been probably asphalt at that level, but in this case, you're basically taking that off, putting a vapor barrier there, your insulation, and then the new roof goes on top. So that's the warm roof build up. In terms of a cold roof build up, you're putting the insulation between the joists down here. So it's just where you have that insulation there. It's basically describing the warm and cold roof solution. As it mentions on the right here, just down at the bottom, flat roofs do have high risks of damp and leaks because of the flat roof. It's never actually flat. It's meant to have a very slight pitch on it in order for water to drain. You don't want standing pools of water on a flat roof at all. You would want it to have some kind of fall on it so that it drains, but they do seem to suffer from, I think, a lot of heat damage. So you get expansion and contraction of the asphalt layer, and then, if they're not maintained or any cracks start to develop over time, they can become quite serious, and that just allows a lot of water straight through into the ceiling level. Heating controls I mentioned as one of the solutions. So we're looking here at a thermostatic radiator valve, very common these days. And then this is an example of a kind of programmable thermostat. So this would be able to you'd be able to program times maybe up to 4 times a day that the heating comes on and off. And then the kind of typical, you might even have zones as part of this programmer. So you might have you want the heating to come on and off downstairs at certain times, and then upstairs and in the bedrooms only maybe once a day. Downstairs you might want the heating to come on 2, 3, 4 times a day. And so with a programmer like this, you would be able to do that. Install costs can be around up to £800, saving you £80 a year. So these are figures from the Energy Saving Trust. The main thing is trying to find one which is actually quite user friendly, in terms of learning how to program them, how to set times. The difficulty is once they're set, you might well not want to change it for a long time. And when you do, you have to get the manual out to remind yourself how to do the changes. Electric heaters. So these are the example of the more modern storage heater. And so here's a bunch of kind of convector heaters or infrared heaters. I think this one's an infrared heater here, maybe that as well. And these are kind of convector heaters and oil heaters. But this is a kind of electric storage heater, a modern, more energy efficient one than the old kind of economy 7 type of technology that you might still find in quite a few homes. Also, this is a good point to remember that tenants should be aware of different energy tariffs as well with storage heaters, because they could be making good use of cheaper energy tariffs at night time to be able to warm up their storage heaters, which then release the heat during the day when they want it. This is also worth noting here. So some properties may not be suitable for gas central heating or heat pumps or solar or other, simply because of the space or access or the type of building, high rise typically, but maybe even low rise. There just might not, it might be a problem installing some of these other technologies, and electric heaters, while not necessarily the least cost, because electricity per kilowatt hour is up to 5 times more expensive than gas, then it's a very easy solution to fit to almost any property. I think that's the point, is that we're a lot of properties you really are restricted in what you can do, then these type of solutions are pretty accessible. When you're thinking about boilers in terms of energy savings, then the older rating of boilers compared to modern A-rated boilers, you can see that the difference now between the D-rated and the modern one is about 160, and one of the older, very old boilers ratings is very considerable. This is a sort of interactive tool on the Energy Saving Trust website where you can look at different types of properties and the relative modeled energy savings. So if you click on these different menu items at the top, it gives you a different kind of profile for the relative savings putting in a new boiler. Low energy lighting, I'm sure this is very familiar, but we've moved away from incandescent light bulbs, which generally emitted much more heat than light. 90% of that energy that they use, the 60-watt consumption rate, was being lost as heat. Compact fluorescents, much longer life than the average incandescent, though there is a story, obviously, that incandescents were one of those products which have a designed life expectancy. Maybe industry designed back in the sort of early days of the electric lighting industry, because they were building light bulbs which lasted too long, and so they built in a certain level of obsolescence so that people would carry on buying them. Anyway, compact fluorescents were offering a lot more in terms of the hours of life. They did contain mercury, which is obviously toxic to human health and other biological life. They used a lot less power, 75% less, and relatively low amount of heat against light in terms of converting that energy. And obviously now we're much more used to seeing LEDs in this kind of format now. Much longer life again, reducing power consumption by 50% again, and really relatively we're looking at 85% less energy use than incandescent. So there's some energy savings relatively. Halogen bulbs are a type of incandescent, which again was something that got introduced a few years ago as a kind of more efficient type of incandescent, but they're generally being replaced by the LEDs these days. Depends on the use, actually. If you're wanting floodlights or other kind of external lighting, I imagine halogen lights might still be used for those in some instances. So these are the efficiencies along here. So incandescents to the left and then LEDs to the right. If we're thinking about the amount of carbon emissions relating to these different types of lighting equipment, that gives you a very stark comparison in terms of LEDs to incandescents. These are LEDs emitting the same level of light as the incandescent. So when we're thinking about renewable systems, heat pumps are kind of being thrown in the same basket as renewables, in the sense that they are much more efficient in terms of heating system, but they're not exactly renewables. They still run on electricity, but because of their technology, they consume what's called the coefficient of performance, is they for a given amount of electricity that they use to run the compressor and fans, they extract and transfer 3 to 4 times that power as heat into the home. But they still require electricity to operate. So they're not a renewable source, but they are a much more energy efficient and what being classed as a low carbon heat source. So considerations for PV. Here's a typical photovoltaic installation. You're thinking about the size of the system, obviously the orientation of the roof it's going on, any potential shading, the roof load capacity of the structure, and whether this system is going onto a flat or sloped roof. If you have a flat roof, you can mount these things on frames which angle the panels towards the sun in a given direction as well. In terms of heat pump considerations, you need to be thinking about the space they're going to be heating, therefore the size of units, the resizing of radiators potentially, because the heat pump is generally operates at a lower temperature than gas boilers, where a gas boiler might be putting out 60-degree heat. Heat pumps typically put out something more like 40, and therefore the heat input to the space would need a slightly bigger surface area of radiator to get the same heating. Air source or ground source heat pumps, if you've got the space to do them, the budget, then you might be looking at a ground source heat pump. And any resident concerns, typically around noise. That's been the big one about these units, but I think they tend to be noisy when they're not maintained. You can get kind of clattering from the fans if objects get stuck in here, and maybe leaves or dust or other kind of obstructions get trapped, and then that can make the fans noisy, or if the motors start to fail and aren't serviced properly. Other considerations in terms of your improvements to EPC C, trickier archetypes. So when you're thinking about the archetypes of properties, you might have a large number of a particular type of house build, and within that you might have certain archetypes. It could be ground floor flats or semi-detached houses or terrace houses or whatever. It's good to be thinking about specialist training to suit the work for those archetypes. If they have certain design features which make doing solid wall insulation very tricky, you need good detailing to be able to do it well on particular archetypes, then that is worth doing if you've got a lot to do. We do have heritage masterclasses on our RISE website which can cover certain aspects of the trickier archetypes themes, obviously to do with heritage type properties. Going beyond EPC C, for EPC B or A, could be other considerations, maybe around net zero, or other more ambitious goals that you might have around sustainability, which could include NFIT, which is, like I said, it's a passive house retrofit standard. Retrofit assessments, they are the PAS 2035 assessment, which is used to develop the long-term retrofit strategy, or medium-term retrofit strategy, I should say, for PAS 2030 projects. Do remember that ventilation is absolutely key to retrofits where you're doing improvements to the fabric of the building, which might include windows, doors, insulation, etc. If you're reducing the kind of background ventilation or drafts, then you will need to be making sure that you have adequate ventilation in place. Otherwise, you'll just get mold. Well, condensation, damp, and mold will be the result if you haven't got adequate ventilation after the work. Remember that the EPC C rating is modelled; it's not an actual measurement. So think about exploring the funding options for retrofit. Remember the fabric first approach, and it's what we covered earlier about improving the building fabric before you change the heating systems. And think about procurement and resident engagement as key aspects of any retrofit project. Procurement in terms of what you're specifying, and resident engagement to get as many people on board as you can. Some other resources on the website as well. So thank you very much.
Thank you, Julian, for your presentation. I hope everyone found it quite insightful and interesting.